Hi guys! So lesson 3 is about rate laws when the data is more realistic. So the numbers don't always look quite as pretty as the idealized ones we did last lesson. I recommend you have a go at these problems first on your own. So when I'm about to start one, maybe pause the video, see what you think the answer is, and then press play and see if you agree with my answer. If as we carry on you feel like you've got it, obviously feel free to fast forward and just catch what the answers are if you don't want to listen to the full explanations, because you can then move on to your set work. All right, so the first few are simply where you have to do a bit of math to work out the ratio rather than simply saying this doubles, that doubles. So, for example, we've got one where Ki is the only reactant, so we don't need to worry about holding something else constant. And it has tripled from 0.1 to 0.3. So that's still pretty nice numbers. I can do that in my head. These, however, 8.4 times 10 to the minus 6, 7.6 times 10 to the minus 5, not quite as straightforward. So I recommend you do what we talked about in the notes last lesson, and you make them to the same power. I'm going to make them both to 10 to the minus 6. So this one I will replace with 76 times 10 to the minus 6. Again, now I need to say what has happened to get 8.4 to 76. It's more than tripled, right? But I'm not confident in that. I probably want to put it in my calculator. So I would do 76 divided by 8.4 to figure out exactly how much bigger it is. And you come up with just about 9. So where the Ki has tripled, the rate has increased by a factor of 9. That's times 3 twice, or 3 squared. So this is second order. So my rate is K times the concentration of Ki squared. All right, our next step in these problems is often to solve for K. So we'll do that now. It would be the rate divided by the concentration squared. I'm going to use trial 1, but you could use any trial you want. And that just ends up being 8.4 times 10 to the minus 4. To work out your units, that's molarity per second for rate, molarity squared on the bottom. So one of the molarities cancels, and I'm left with molarity to the minus 1 seconds to the minus 1 as my unit for K. All right, let's have a look at another one. In example 2, we do have 2 reactants, so we have to look for where the concentrations were held constant. This is more realistic. Look at it, the numbers aren't perfect. They tried to hold it constant, but that last digit changed by 1. That makes sense. It's our least significant digit. Same thing over here. The last digit is changing, even in the rates. For experimental data, 1.08 and 1.07, they're close. They count as the same, right? These are real reactants, real rates. You're not going to get perfect data. Right, so when I'm looking for one that's held constant between experiments 1 and 2, we can say A is constant. B has done something. If you're not confident in it, put it in your calculator. So let's say B, if I put 0.137 divided by 0.034 in my calculator, I get 4. So it's 4 times bigger. It has quadrupled. What has happened to the rate? Again, you might just want to put that in your calculator to do yourself a favor and make it so there's less that you have to type, or if you're on multiple choice, it may be worth your while to change these so they're all 10 to the minus 4 for faster comparisons. So I just moved that decimal over twice. This would then turn into 108 compared to 6.67. So if I do 108 over 6.67, I get 16. The rate is 16 times bigger. Okay, this is very similar to the one we just did. 16 is 4 squared. So what we did to the concentration of B happened twice to the rate. Second order. With respect to B. All right, let's look at A. We need ones where B was held constant. So that's trials 2 and 3. What happened to A? Oh, look, it's exactly the same. 0.034 to 0.136. It's times by 4. That's convenient. And the rate? Oh, look, it didn't even matter. The rate was constant. Lovely. Love when that happens. You don't have to do any math. It's 0 order with respect to A. So we can write our rate law. Rate equals K times the concentration of B. No A needed at all because it's 0 order. And solve for K. I'm just going to use trial 1 again. Rate divided by B. Oh, second order, sorry. And that gives me 0.577 units. We've got molarity per second on the top, molarity squared on the bottom. It's exactly the same as last time. That's not a coincidence. Every time your overall order is 2, these will be your units. You'll find some resources on the web where they have you memorize order 1, this is the unit, order 2. I don't think that's worth your brain power when it's not that difficult to work out. If you feel like memorizing them, all the more power to you. All right, example 3. We've got one reactant again, but these numbers are atrocious. It doesn't matter which ones I pick. They're all sort of just as bad as each other. I'm going to go with the first and second, just because they're at the top. So I need to work out how much bigger is the N2O5. Well, I can't do that one in my head. So 0.190 divided by 0.0750. Let's find out how much bigger it is. Put it in your calculator, you get 2.53. So there's a weird number for you. That's realistic. That's what you get in the real world. If you guys are in a lab, that's what happens. Let's see what happened to the rate. 2.26 times 10 to the minus 3 over 8.90 times 10 to the minus 4. I put that in my calculator. Oh my goodness, 2.53. So the numbers may have looked messy, but once you do the math, it's actually fairly straightforward. What we did to the concentration, the exact same effect happened to the rate, so it is first order. My rate law. K, let's just sub in trial 1. And when I put that in my calculator, I get 0.0119. We need some units here. Molarity per second divided by molarity. It's just seconds. Done. Okay, we got a really fun maths extension here. What you saw me just do above can be explained mathematically using this equation. I did the concentration over the concentration to figure out what factor it had been increased by, and I did the rate over the rate to figure out what factor it had increased by. But then we just used inspection to work out the order. We didn't really use a mathematical function to work out the order because our orders are usually quite simple. 0, first, or second. There are times when the orders aren't that simple. Some reactions have fractional orders. You can have something that's half order. You can have negative orders. There are exceptions in the real world. So a chemist will use this equation to get an actual figure for the order. That's also true if your data just doesn't work out quite right. It'll give you an order of 2.1, and you can say it's approximately 2. Just for kicks, because I think it's awesome for you guys to see where this comes from and to link what you do in chemistry to math, I am going to work through the proof of this with you. If you're not interested in logs and you don't want an extension, please feel free to fast forward the video. All right, so let's look. We have the rate equation. Looks like in that form. Rate equals a rate constant times the concentration of the reactant raised to some power n. That's our reaction order. This should be true for every trial. That's the whole point. It's an equation that relates rate to concentration. So if it's true for trial 1, it should also be true for trial 2. The only thing that stays constant is K, which means if I rearrange for K, I should be able to set the top equation equal to the bottom equation. So, for example, K on top is equal to rate divided by the concentration to the power. Well, that same expression works for trial 2, and they should be equal to each other because they're both equal to K. Now I can solve for n. So I'm going to rearrange this by putting both the concentration to the power n terms on the same side. Rate 1 over rate 2 equals concentration at time 1 to the power n, concentration at time 2 to the power n. All right, when you have this, let's first of all simplify it so that we only have one exponent. When you solve for an exponent in math, the trick is to take the log of both sides. The reason that works is because of your properties of logs. If you take the log of something to a power, you can simply remove the power, put it outside the log, and multiply it. So how that will look is I'd end up with the log of rate 1 over 2 equals the log of x1 over x2 to the n. That n can come right out front, which gives you log rate 1 over rate 2 equals n times the log of the concentration of x1, concentration of x2. And lo and behold, you have our equation. Before I solve for n, I'd simply divide by the ratio of the concentrations. So there you have it. That's a mathematical way to figure out the order. If you're looking at AP scoring guidelines, you will actually see that sometimes. You're going to be amazed. They accept this as evidence of reaction order. I think you'd be crazy to do that when you can write something as simple as when A stays constant and B times 2, the rate times 2, and they give equal marks for that.